Okay, well, welcome everyone to the Topos Institute Colloquium. Today we have Georges Gonthier talking about foothills and cathedrals, organizing the libraries behind big proofs. So please, Georges.
Thank you. Well, thank you very much for having me, hosting me tonight, or this afternoon for the people on the other side of the pond. So I'm going to talk about something which has been a passion of mine for the past 20 years or so, which is hacking mathematics so to make them fit into a computer. And so this is basically my contribution to the area of formal proofs. So here's a somewhat shortened history of computer proofs, starting with the granddaddy of all of them, which is the four-color theorem. And then starting a little later, around the 2000s, you have results that are actually proven using computerized proof systems. Now, some of these results are new results where the proof was actually given by the computer, and some of them are just revision on a computer of something that was done before. And my contribution, that rectangle is not in the right place. My contribution was the four-color theorem and the odd-order theorem, and that's mainly what I'll be picking my examples from today. So I got hooked on this subject by first actually applying computer proofs to computers and doing something called the camel garbage collector. Then 10 years later, I thought it would be fun to try this after real math, and I had this long-time fascination with the four-color problem. And so I tackled that and got a bit noticed for this, which gave me license to try something that was a little more real math, which is the odd-order theorem. So you'll get a little bit of all of those today. So I'll start with the sort of granddad of computer proofs, which is the four-color theorem. So any planar map can be colored in four colors, so that in such a way that adjacent regions don't have the same color. So the way the proof works is you use the Euler theorem to figure out that the average number of sides of a region is less than 6. So you look at an area of the map where the average is lower than 6. You pick a specific configuration. So in this case, you would be looking at a map with just a pentagon in it. And you look at you do a calculation of all possible ways of coloring it and figuring out that the coloring can be adjusted to reduce the map at that at that configuration. So that proof outline with one submap, one configuration, and 3 colorings was the infamously failed proof by Kempe and Tate in the late 19th century. So the real proof looks at a much larger number of submaps, looks at a slightly smaller number of configurations, and then a huge number of colorings, because as soon as your configuration gets a little larger, the number of colorings grows exponentially. And so it actually took a computer to carry out to examine all these colorings, because you need to look at 10,000 submaps, 1,500 configurations, and over 1 billion colorings. So at the time in 1976, that was done with a IBM assembly language program and required 2 months of mainframe. So specialists were happy with the proof, and the lay mathematicians were split between the ones that didn't quite buy the analysis of 10,000 submaps in a couple of hundred pages of text, and the ones that didn't trust an assembly program which they couldn't examine properly. The situation improved in 1995, where basically using better computers, you could actually process the map analysis part so that all of the proof was done with a computer. Still use fewer configurations, but still about the same number of colorings, and then this ran on in 3 hours back some 30 years ago. And my improvement on this was to replace the C programs whose meaning was not exactly well defined with something that was a little more mathematical, programs written in basically a subset of lambda calculus that has a clear mathematical semantics. And then using the same system to actually prove the program's correct, and still using the same system to prove the setup for the computation correct, so that basically all of the proof could be verified, and you didn't need peer review to know that the proof was correct. And it ran in an hour and a half some 20 years ago. Now it runs in 15 minutes, of course. So the whole proof is this: look at, find the set of configuration that's unavoidable, so that in any planar map you're guaranteed to get one of them, and each one of them has this property that it allows you to carry out basically an induction step, and verify that the combinatorics fit. So where does this, this was my first lesson in figuring that there's a difference between mathematics on the printed page and mathematics that works well if you're going to do everything formally. Because if you do everything formally, then all of the details have to click and have to work together. And this was very apparent in the four-color proof, because the key notion of the four-color proof is the notion of a map. And the sort of traditional description of a map is to say, oh, well, we have this picture where we've got lines connecting dots together, edges connecting dots together. So nodes, edges, that's obviously a graph. But then to make it planar, you have to explain that there's an embedding into the real plane, and then things get really messy, because now you have to invoke the Jordan curve theorem to use the fact that it's planar, and things get horrendously complicated. So I realized fairly quickly that if I was going to do this, I needed to find a better way. And the better way is a really neat trick, which consists in, instead of having big blobs where the edges connect, put little blobs at the corners, at each corner. And then you can connect the blobs around every region of the map. And you can connect the blobs with another color around each edge intersection. And if you look closely, you can add a diagonal across every red and green square, and then you basically have a one-to-one mapping between the edges and the blue cycles, and the regions and the green cycles, and the nodes and the red cycles. And this structure is something I rediscovered, but that's known as a hypermap. And they're real cute because they're actually symmetrical between the edge nodes and faces. So in terms of reducing the work you have to do and doing a proof, it's really nice because you get these symmetries that let you prove theorems once. And the planarity condition is basically the Euler formula, which is with this presentation becomes is also symmetrical between edges, nodes, and faces. So the case in point that this is the right way of doing this is that at a key in the revised proof, so the one that is was recognized and as being the neatest and the cleanest, there's this one critical point where you need to describe the relationship between a configuration and the map it's embedded in. Then you have to come up with this projection that materializes the embedding of the configuration, and the proof that there's this embedding is basically folklore. Literally, this is a text, and it's probably the right way of doing this, because if you're going to have this notion, this mixed notion that says it's topology, it's a mixture of topology and combinatorics, indeed your proof is extremely messy. If you have the right mathematics and you organize your details properly, then it's just a 4-line definition, and it's just easy because you just have in your mathematical description the way of navigating around the map. And having the details right is really important because it affects what is reasonably feasible and what is unreasonably hard if you're going to do a formal proof which every detail is catered for. This is this notion of hypermap comes with its own version of the Jordan property. So, which is important because this is the thing that allows you to basically cut out a configuration you've identified. When you've identified a contour, you can cut out the inside of the contour. So there's this is obvious if you're doing it in a plane, or it requires the Jordan curve theorem. There's a combinatorial equivalent, and so this is obviously the key lemma of basically this entire part of the proof. And the proof of this lemma is about 100 lines, so longish but manageable. If you have set up your definitions the wrong way, and I actually have an example of this because the same presentation, similar presentation was used later by the FlySpec project, trying to prove do a formal proof of the Kepler conjecture. Then you get something that has basically 1,600 lines of proofs instead of 117. So you get over it a 15-fold explosion in the work you have to do. Now, Tom Hales managed to do this because he could hire a bunch of Vietnamese grad students to do the work for him. But I think it's cleaner to do things the right way. So on to I'll put a pin in the four-color theorem because it's going to make a return later in the talk. But I wanted to move to a more classical topic, which sort of gave the title to the talk, which is the odd-order theorem. Now, the odd-order theorem is sort of the main the first big mountain or the first cathedral in this huge cathedral of modern algebra, which is the classification of finite simple groups. So the auditor is sort of doing half of the job. It says, okay, I'll classify the simple groups that have an odd number of elements, and this is simple. The only ones are basically the prime cycles, or the and an equivalent way of saying this is saying that all groups of odd order are solvable. And the interesting thing of that proof is that in order to get to this proof, to get to this mountain, you had to go through all the foothills of a sort of standard algebra curriculum. So you had to learn about polynomials, linear algebra, Galois theory, and then some more specialized group theory topics like character theory, Thompson factorization, and Frobenius groups. And what we quickly learned was that we weren't even at that stage. In order even to get to that stage, we had to go through the anthill before the foothill and just do very, very basic things like CELO theorems and canonical isomorphisms. And we realized that we first had to figure out ways of doing these very simple pieces of math well in order to have any chance of doing the harder math. So this was a very much a learning journey. So to give you an idea of the relative sizes, the original proof by Feit-Thompson basically was 50 years in the making, and was about 250 pages. I mean, the theorem was first conjectured around 1913, so 50 years before a proof was found. And it took about 20 years to actually proofread the original proof and sort of get all the kinks out and get all the bugs out. And so there was a revised proof that was published 20 years later. And the revised proof improves a number of things, but also spells some things in a little more detail. So the upshot is that it's about the same length. And the computer equivalent of that proof can be stated in a way that looks very much like the original text description. And it has this nice property which it shares to some extent with the four-color theorem, that this is one of the theorems where the definitions you need to be able to state the theorem are really, really short. Like you need about only 50 lines of formal logic, starting from absolutely no background whatsoever, no arithmetic, just describing groups and solvable groups and so on. And so this is the only part you have to look at if you want to be sure that the theorem that was that's stated here is actually really the odd order theorem, and I've not somehow redefined odd to mean trivial, which would then make the theorem rather uninteresting. And the proof is roughly 45,000 lines of formal logic. And my estimate is that it took about 2 years to write the proof itself. But there was an additional 4 years in order to write the library that the proof rests on. So the proof goes into, I'll just give a brief overview of the proof. It's basically split into 3 unequal parts, 2 big ones and a little coda. So the first part is just looking at the subgroups of, so you assume you have a minimal counterexample. So since it's minimal, it has the property that every subgroup of it, proper subgroup, is solvable. And lots of things are known about solvable groups. So we can use all of those properties to figure out what shape the solvable groups have. And the upshot of the analysis is that if you look at the maximal subgroups, so the ones that have no proper supergroups except the counterexample itself, then they have a very specific structure of being basically a Frobenius, what's known as a Frobenius group, and I won't get into the details of this. But because they have a known structure, they have their characters have also a known structure, and the characters have this property that they have this Euclidean structure, so they have a geometrical structure, and there are isometries that link the characters of the subgroups to the character of the original counterexample. And if you combine all of these isometries, you can get a basically a norm inequality over the entire group. And that norm inequality is impossible. So that's your proof, or that was the original scheme of the precursors of the Feit-Thompson theorem. It turns out that if you actually want to prove the outer theorem in the fully general case, you have one nasty subcase that escapes this inequality, and it has a structure that basically combines Galois groups. So you get the additive subgroup of a given Galois field, and then the multiplicative subgroup of that Galois field that acts on the additive group, and then the Galois group that acts on this. And the order of that prime field is p to the q when p and q are where p and q are prime. And so you get groups with p to the q and another group with q to the p. And at this point, all of your inequality machinery and geometry machinery fails, and you have to switch gears completely and turn to Galois theory. And turn basically the structure of these groups into polynomials. And these polynomials tell you that, so you get a polynomial degree q that has p roots, which tells you that p is less than q, but then because this is symmetrical, you also get q less than p, and this is your final contradiction. So you see that in order to get those, so the revised proof was published as 2 volumes in the LMS notes series. And in order to formalize these, you actually have to formalize all of the curriculum that goes behind this. So you get basically a whole library shelf into the computer, with just a little thin part at the end being the actual theorem you want to show. And the actual representation of how this works is looks something like this. So this is basically the mathematical library we developed, and it actually splits visually in a nice way, where the little basis down here is the combinatorial part of, so the very basic part, the pencil and paper math part of the library. So you don't think when you teach mathematics of teaching how to use pen and paper, but basically a computer needs to be taught that. And so that part is what goes into basically the four-color theorem. Then all of these parts here are the components of the library that basically encode an algebra curriculum. And then this tower that comes on top is the cathedral of the Feit-Thompson proof. And to give you an idea of scale, so if you just zoom in into one of these little blobs, so each blob corresponds to a couple hundred lines of formal math. So one blob talks about basic properties of prime numbers, and one blob here talks about finite groups, and you've got blobs talking about morphisms and quotients. And so the finite group blob starts with this description here that tells you everything that's been defined in this. So you can think of each of these blobs as being basically one course, one undergraduate or graduate course for the blobs that are higher up. And the one of the differences between this and a more standard textbook is that you actually need to teach the computer how lemmas in the way that they are actually used. And so given what would be normally presented as a single result, like the Lagrange theorem, you might get into a bunch of corollaries expressed as a bunch of corollaries, because each one of these turns out to be useful in practice. And so this is the basic part of the library. All of the proofs are really, really short, like the actual proof of the Lagrange theorem is just 5 lines. And most of the corollaries are derived in a single line. Now, more substantial theorems, like this is the theorem taken from the revised proof that describes the basically the exception to the Frobenius type group. So the one where you have which turns out to be in the end a structure based on finite fields, groups of finite fields. So this is the actual text, and this is the formalized version of it. So they're pretty much the same size, and if you at the time I wrote this, wouldn't have fancy characters in the system. I must say that computer-proof systems have progressed much in the past 15 years, so we're much better than this now. But if you can read LaTeX in source, you can pretty much read this as the original one. Now, where there's a fairly good mapping for the actual statements, which is important because at least you can tell the things you proved. For the proofs, the language is quite different. So here's the proof that one theorem is about 4 pages. So here are two of those pages. And this is, again, about half of the formal proof of the same theorem. So it looks quite different. But and that's because a proof in a textbook will just give you highlights of the important steps of the proof, but not actually tell you how you get from one highlight to the other. Usually we have this, and then you can see we have this. You tend to have to be more precise in a formal proof. On the other hand, you don't have to give all of the highlights, because once you've given the instructions to the computer can figure out the highlights. And so one of the nice things it can do is if you do proof by induction, it'll figure out exactly what the induction hypothesis is. Whereas if you were reading the textbook proof, you'll often have induction as an afterthought, and then you have to figure out exactly, if you're doing actual proofreading, trying to verify the proof, you have to figure out exactly what the intended invariant was. And it's not always obvious, and indeed not always correct. There were a few bugs left even in the revised proof. So let me now go a little show a somewhat easier example of a formal proof that's a little more relatable than the pure combinatorics of the four-color theorem. So my favorite example is the fact that the matrix product commutes under trace. The traditional textbook would say, okay, well, define the trace as the sum of the diagonal elements. And so we expand this definition, then expand the definition of the general term of a matrix product, exchange the two summations, commute the scalars inside the product, and then basically undo the expansion you've done before, and now the proof is done. And if you look at the completely formal proof of this, it's about the same size. It's 4 steps. So the one thing we'll do, and so the way you'll do the proof is the system will tell you, okay, well, you have all of this context where you have integers n and m, and then you have A that's an m by n matrix, and it's figured out on its own, since trace needs a square matrix, that B is an n by m matrix. Now, since we want to use this expansion twice, we actually want to prove it as a separate lemma, and so we can say basically prove this for A and B, and then have this generalized so that we can use it in both directions. So now we'll have to show the expansion formula. And this is done as simply by expanding definitions. So nothing much to show here. And then we can use this twice to expand both sides of the equation simultaneously. So we don't need to, we can sort of burn the candles by both ends. And now we get 2 very similar sums, except the internal terms need to commute, and then there's just one line to do this. So that's a nice proof. But what makes the proof tick is the fact that we were able to write these sums, and they had a minimal amount of information in them, so we can actually read the sums. But it's not so obvious to translate this concept of a generalized sum in a way that makes sense for a completely formal system. There's actually a lot of detail that's being hidden in the notation. And so there's this whole machinery in the library that deals with basically all kinds of iterated operations. So it can be sums, product, GCDs. And for example, you can define the determinant with this particular summations, where you have both a sum, a product, and you sum over permutations. So let's see how that's really implemented. So this is the actual definition of trace. So nice expression, you sum AI over I. But really that nice bit of a string of symbols expands into text that has lots of holes in it. So there's a lot of missing information that's not being typed in, and which the formal system has to figure out. So a sum is understood as iterating some form of addition, where the last the empty sum is 0, and since we haven't specified a range, we're going to enumerate all of the index type, and here is the thing we're iterating, which is just the diagonal function returning the diagonal elements. Now, one of the features of most formal systems is that they have a type system, so they can figure out from the declarations of variables and the way you are using them, what kind of objects there are. So this is the same thing you have in the standard programming language, where you can tell integers from floating point numbers from characters or bitmaps. So in this case, the types can go a long way of figuring out that, okay, the type over which you're iterating this addition operation is this type R, and then the range you're iterating over is basically the range 0 to n-1. So this is a specific type, and then you're interpreting the matrix as a function that gives its coefficient. But in order to figure out, that doesn't tell you what the zero means and what the addition means. In order to figure that out, you need to know about the structure of a ring, so that this type here really is a ring and it has properties, and that's done through an algebra interface. Basically, you've got a way of telling what operations you have on a given type, and this also extend to also giving properties of functions over these things like morphisms and so on. So in this case, the plus really means that you're going to get the addition operation for the addition subgroup of that ring, so part of these interfaces are something you would find in the textbook. And then you've got interfaces which are definitely not from a textbook, like basic combinatorial things like figuring out whether two things are identical, or figuring out how to enumerate a finite type. And you would this is basically the maths of pen and paper. You think those are things are too trivial to do an undergraduate course on them, but they're vital if you don't want to have a computer system that feels like it's totally stupid. And they're useful enough because these are the only interfaces that are being used to prove the four-color theorem, apart from the hypermap interface. So with those matrices, you can figure out how to enumerate this ordinal type here, and you can see that there's quite a gap between what you actually type in and what's needed to make logical sense of it. So to summarize, you've got all of these interfaces that let you build big operators. So it's those interfaces, both standard mathematical ones and non-standard ones, that let you organize a library that's flexible enough and expressive enough to do some serious mathematics. Again, the key things is the little math. So perhaps a more another example of this, which might be a little more mathematical, is just the idea of how to define group theory. So here are a bunch of standard group theory notions, like being a subgroup and taking a normalizer and having normal subgroups and constructing factor groups, having morphisms, and so on. And then you have also operations that you apply to subsets of groups, which are not necessarily groups, like pointwise multiplication, or taking the identity element of this, which is the trivial group, which is also notated 1. And then you've got operations that apply to the actual elements, so multiplying, taking the unit element, or taking inverses. And The point of if you were going to go the way of the sort of commutative algebra interfaces we had on the previous slides, you'd say, okay, well, I need to have a separate type for each group. But you're not going to do a lot of group theory that way, because most of the proofs you do about groups you have multiple groups that share elements. And by definition, or by construction in logic, types are disjoint. So groups are not types. And group theory is kind of really of a misnomer. Group theory should really be thought as subgroup theory. And in Calc, you can sort of do this. You can say, okay, well, I'll define a property that tells me when a set is a given group. The nice thing is that we can use interfaces to give properties to certain sets and tell that these things are actually groups, and then they will behave as groups when you do the theory. And the nice thing about this is that your theory becomes a lot simpler, because now you've got an absolute notion of what a normalizer is, and you don't need to localize normalizers. So it really simplifies your theory, and multiplying sets and multiplying elements are just the same thing from the point of view of this theory. Likewise, quotients get also an improvement because you realize that there's this important side condition for quotients that says, oh, you can only divide by a subgroup by a normal subgroup. But that condition is really not needed mathematically. It's sort of like dividing by zero. You impose that condition in order not to make errors when you're applying isomorphisms. If you have a formal system that's checking the operation you're doing, you don't care about division by zero, because the proof system will prevent you from simplifying by zero, which is the actual thing you should never do. And in this case, you can define the natural definition of quotients, which is just the image by the standard coset morphism. Tells you that G divided by H is this construction, where you actually restrict G to the normalizer of H, and then quotient by the group generated by H, and that definition is so this is the actual meaning of the definition, and it actually simplifies the proofs quite a bit, because if you look at group theory textbooks, you actually see this expression all over the place. So because we're doing formal math, we actually can improve the maths. There's a similar thing that happens with characters. So again, characters are functions that map group elements to complex numbers, and they have this property of being constant over conjugacy classes of a given group. So these are called class functions, and characters are a subset of the class functions that have integer coordinates or non-negative integer coordinates. If you define characters this way, in the same way as you define groups, then life is going to be painful, because you will end up having to specify every time the group over which you want to do geometrical operations like computing dot products. If you're a little smarter, you can make an intermediate interface for class functions. This is not something you'd find in textbooks, but if you read the textbook with the right view, then you'll see that this is the right way of doing things. And when I realized this, I think all the proofs I was trying to do became basically half the size. Let me use the last 5 minutes to talk a little more about hacking proofs. What I've been describing so far is how to basically change meaning, but you can also use the fact that you have these formal constructions to use large-scale automation to basically simplify arguments or encode the fact that you're going to use a specific proof method to discharge proofs that would be very painful to write in full detail. So there's a lot of this going on in the four-color theorem. The reducibility part is an algorithm done by a proof algorithm that's called model checking. The unavoidability part is done by something called combinatorial search. And the link between the two is abstract interpretation. And all of these have very important industrial applications for software. An example of sort of these large-scale computation is computing this reflexibility. So this can be completely automated. So you just write this one function that does an extensive computation, and then you prove this one logical property that if the operation succeeds, then the configuration is actually reducible in the mathematical sense. And then if you want to prove that a certain configuration is reducible, then it's just a one line. You just say, okay, compute, and everything goes, and you just have a trivial proof that covers 20 million cases. So the little language you saw here to describing configurations is something else I think I'll have to skip over, but it basically uses an interpretation that computes where each letter corresponds to a little piece of that you add to your map, and then you can interpret these sequence of letters in order to figure out how to color a given graph or how to do other operations. So the model checking is just this algorithm, and then you can use this abstract interpretation and combine it with the reducibility check to come up with your own specific logic. And so this is the logic that's used to do the unavoidability part. So there's this basically specialized language that was invented for the revised proof, and that lets you carry out very efficiently this combinatorial argument. Now, lest you think that this only happens for purely combinatorial proofs like the Otto theorem, there is one instance of this in the Feit-Thompson proof, where we're trying to extend an isometry from a given submodule of characters of a subgroup to characters of the entire to all of the characters. And the submodule is generated by a certain family here. There's a trivial solution, and there's a question of whether the solution is the right one. And so it's basically an integer norm problem. So you can infer basically these integral vectors from the dot product, and you'd think that this was basically you have to analyze a 2x4 rectangle of characters. So you'd think that just doing naive brute force computation would solve the problem, and it just doesn't, because this is actual math. So there's lots of symmetries going on, and this just fails miserably. And the way this is solved in a textbook is by figuring out this nice little algorithm that has a special language that has that lets you write this combinatorial proof. And luckily enough, if you do the same thing we did that was done for the four-color theorem, then you can basically mirror that argument and have a formal proof that looks very much like this specialized textbook proof. And the formal definitions for these things are basically trivial, so they're just a couple of lines each. So that makes me finish about on time. So the my takeaway message is that the computer systems can be taught to do math in a practical way, and doing this isn't just purely an exercise in hacking. It actually teaches us new ways of looking at maths and possibly even new mathematical ideas. So it's quite a fruitful exercise, at least it has been for me. And with that, I'll
Okay, thanks, George. Are there questions from the audience? Sorry about the echo there. We're watching it all together, and I have my computer here too. I'll just move to another room. But if someone has a question, actually, there are 3 questions with people with hands up. So just go ahead and maybe Andreas.
Okay, this is not specifically about your talk, but about some concepts that came up during the talk. You mentioned in connection with these computer understood proofs, the contrast between highlights, which is what would interest us, and I think you said trivial but vital details that might not interest us, but are needed for the computer to know what's going on. Of course, different people may put the dividing line in slightly different places, but there are some things that we would probably all agree are important and some things that we would all agree are trivial. My question is that distinction something that can be detected or at least approximated by some kind of computational process? Can a computer extract from the proof things that it thinks are likely to be interesting to us?
Well, the writer of the proof tends to do this. It's just that the standard way of writing proofs tends to emphasize the what at the expense of the how. And this is maybe done as a way of teaching math, because you say, oh, you have this, and then figure out you have this other thing follows from it, and figure you should be able to figure out how to do this, and so on. Whereas and to some extent, you can do this with a computer. You can say, okay, you want to prove this, and then you want to prove this, and then you want to prove this. And then to go from one thing to the other, use combinatorial search, or even these days AI, to figure out how to get from one part to the other. And that can be done, but somehow it's I think it's more satisfying if you're writing down the proof. You actually know how you get one place to the other. So it's you realize that there's some places where it's actually better to give the how rather than the what. And the person reading the proof can still get the what, because the computer will figure out what was the result of applying commutativity, or drilling down to common subterms if you're trying to prove an inequality between, say, formal sums that have the same range. Or if you're doing an induction, the computer will figure out what the induction hypothesis is, for example.
So
so that's so it's I guess you could try to figure out, automate the exercise of trying to figure out the highlights. It's something that for the proofs I've worked on, I tend to do by hand. So if you're working on a proof, you'll tend to focus overly on the how. And then you sort of read yourself and say, oh, well, actually, there were these highlights. And maybe I can refactor my proof so that the highlights are more visible. And often when I do this, I get a much better proof. Indeed, a shorter one, for example, or for example, I'll realize that there was this one property I've proved 3 times over, in various subcases, and whereas I could have used this little tool I showed to just prove it more generally, just once for prove it in one case and then generalize it immediately.
But these improvements that you're talking about are things that at least for now you have to do. It's not something that can be automated.
Well, I guess it's in the eyes of the I'd say it's in the eyes of the beholder. And to some extent, if you're the better you get at this, the less you need to do these, or the improvements need to be less extensive. Right. Because you can you sort of learn not to do silly things, or you realize if you're going to do the same thing twice, that you're actually I think I remember doing this before, and you sort of refactor immediately rather than writing a 2,000-line proof and then figuring out how to compress it back to 200 lines.
Well, let's see. Thanks for the question and the answer. I think let's see if we can fit one more in before the
Thank you.
hour. Thanks, Andreas. So Valeria.
All right. I think it's a sort of similar question, George. If you go back to that slide where you had basic interfaces, kind of general libraries for undergraduate, and then the pinnacle. Feit-Thompson thing.
Yeah.
I think my question is whether the ways one does things in the computer, you need to know what is the pinnacle that you are aiming for. Yeah, that's the mathematical shelf. The question is, should the black bits be done once and for all for all kinds of mathematics, or do they actually only work for the Feit-Thompson? And
we tried rather hard to do the black and blue bits so that they will work for a range of things. There were some simplifying assumptions we did. So, for example, all of the group theory that's being developed is finite group theory. So there's no attempt to merge it to infinite group theory, because there's practically there's no use for it in this development. And if you look at it from from far enough, the overlap between finite group theory and infinite group theory is rather small. It's sort of you're actually doing rather different things if you look at finite and infinite groups. So we tried really hard to have the components be as generic as we could make them, and I think we've been rather successful. So they've been reused since so that proof was finished 10 years ago, but it's been The library has been used all over the place since, and of course, the lower you go in the library, the more reuse you get. It's the simplest things that get used the most.
Can I have a quick follow-up, David? I mean, do you think the components, we can kind of build up the components for the whole of the math undergrad degree, kind of, you know,
Well, that's certainly what the people, the community, the lean community has been working towards. The specific the nature of Coq means that it's a little harder to do analysis well in Coq than algebra. So you sort of get more bang for your buck if you're doing algebra. Although there's been interesting work in trying to get Landau notation to work more properly inside this library, for example.
Thank you.
Well, let's stop here and end the recording. Thanks again, George.